Good morning, all of you. So I welcome all of you to the second day of the national webinar organized by Department of Chemistry, Parampur University.
So I request Head of the Department, Dr.
Pamankan Godne,
to start
to start the proceedings of the day.
Thank you, Dr. S.N. Sahu. Good morning. Namaskar. This is the second day of the national webinar, Recent Advances in Chemical Sciences 2020-21. And the first session of the second day of the national webinar, I, on behalf of the PG Department of Chemistry, Parampur University, on behalf of faculty, staff, and students, I welcome you all. I also specially welcome the speaker of the session, Professor Santosh J. Gharware, to this session. At the same time, I welcome him to come to visit our department in your near future. Sir, this is my personal request. You please give some after Corona. You please give at least 1 or 2 days to visit our department. We will be happy. Our students will be happy. Anyway, I once again welcome you, also all the participants, to the second day of the webinar. I request Dr. S.N. Sahu, convener of this webinar, to give the brief introduction of Professor Gharware and continue the process. Thank you all.
Thank you, sir. So, thank you for giving me the opportunity to introduce the speaker of the day, Professor Gharpure. So, this is a short biography of Professor Gharpure. So, Professor Gharpure did his masters in chemistry from IIT Bombay in the year 1996. He obtained his PhD degree in synthetic organic chemistry from Indian Institute of Science, Bangalore, under the guidance of Professor Sri Krishna. Then he moved to Indiana University, USA, for his postdoctoral research with Professor Evans. He joined the Department of Chemistry, IIT Madras, as an assistant professor in the year 2004. In 2012, he moved to IIT Bombay as an associate professor. The position of professor. He is also the professor in charge of social and entrepreneurship, that is known as SINE, IIT Bombay's technology incubator. His research focuses on organic chemistry pertaining to natural and unnatural product synthesis and developing new synthetic methodology. He is also working on problems relevant to industries from different domains. Professor Gharpure is a recipient of INSA Medal for Young Scientist. He was awarded with IIT Madras Young Faculty Recognition Award for his contribution in teaching and research in the year 2010. He received B.M. Birla Science Prize in Chemistry for the year 2011. He was selected as one of the Theme Chemistry Journal awardees for the year 2013. IIT Bombay conferred on him the Excellence in Teaching Award for the year 2015 and Departmental Award for Excellence in Teaching in the year 2019. He was selected for the award of CRSI Bronze Medal in the year 2018. So far, he has guided 8 postdoctoral students, 15 PhD, and 16 MSc students. He has 3 patents to his credit and has published more than 70 research papers, having very high impact factor. Personally, I am very fortunate to be the student of Professor Gharpure. Actually, I did 2 courses during my PhD at IIT Madras, in which Professor Gharpure, he was the course coordinator. And he is one of the finest organic chemistry teacher I have ever encountered. So we are very fortunate to have a speaker like Professor Gharpure, and I hope the participants will definitely enjoy the real beauty of organic chemistry from people like Professor Gharpure. And today he will be speaking on new strategies for synthesis of oxa and azacyclics. So with this brief introduction, so I welcome Professor Gharpure. Kindly go ahead with the presentation. The diet is yours.
Thank you, Sahu. I mean, you take me back to Madras days with that introduction, and I still recall, teaching the courses to all of you. And if I remember, it was a corner room, and then we all used to kind of sit there and go through the chemistry lessons, typically slightly advanced level ones because you were a PhD student. But you bring back those fond memories. Before I begin, let me thank you for this kind invitation. This is actually a virtual visit for me, but I also want to thank Professor Mishra for giving me an invitation to come down there. And I wish that I will come back there in a physical mode as well when the situation permits. But just to kind of assure him that that will be my second visit to Behrampur, not the first one, because if I recall, I think 2017 there was a conference and I had visited, and I have very fond memories of that visit. So I always look forward to coming to that part of India because I have seen many students, including students like Sahu, who come from this region, and they have done fantastically well. I was fortunate to have 2 of my own PhD students coming from Orissa and who have made significant contribution. In fact, today's story, what I'm going to tell you, does involve Santosh Nanda as one of the main players. So I hope that you will enjoy that lecture also from that angle, that one amongst you actually could come and contribute in the research programs in IIT. And hopefully that serves as a motivation for the younger lot to take up challenges in research and contribute in their own way. So let me share the slides. A second. Is it visible? Slides are visible?
Visible.
Right. Okay, good. Okay. So what I'm going to do in next 45 minutes to 50 minutes is I'm going to tell you actually a journey of our research, how the chemistry evolves. When you start your journey in research, you may start with something. Along the way, while you are exploring the unknown landscape, you may come across some opportunities which are created because you look at the challenges which are there as opportunities. And when you take those challenges as opportunities and build up chemistry around it, that path can also be equally rewarding. So I have kept the title very general because that's the kind of landscape that I'm going to try and show you. You all know that typically synthetic organic chemistry will always look to the nature, just like any other science person, and try to get inspired from there. And one of the ways in which organic synthesis evolves is by targeting natural products. Now, if you look at the collection of natural products that I'm showing on this particular slide, you will find that they are not really daunting natural products in one way. But if we ask total synthesis person, the person will say that every natural product is challenge in itself, because now no matter how simple it looks like, it's always very difficult to complete the total synthesis. You may be able to make a skeleton, you may be able to put some functional groups in place, but finishing total synthesis has always been a challenge. And I can assure you, based on my own training in this domain, that any total synthesis is always challenging. So what is the reason for collecting this molecule on this slide? The reason for that is that we take inspiration from nature, from the natural products, because they provide you opportunity to develop strategies. But like what Koresh said, that many a times that the target that you choose should have a purpose. These natural products which are there on the screen had a purpose, and that's why they are there. And that is because the main program of our research group was trying to develop strategies for heterocyclic compounds. And when we were developing strategies for the heterocyclic compounds, we ended up also using our homemade recipes for synthesizing these natural products of different types. What is the common theme in these natural products? Number one, like I said, they are all prepared using the methodologies which were developed in-house. That is, we developed the methodology and showcased our methodology in synthesis of these natural products. The second thing which is common in all of them is at least one heteroatom is present in each one of them. Okay, so you can see that oxygen or nitrogen, one of the two will always be present. And in some cases like Chelonin C, you will see that both the heteroatoms are present in this particular kind of molecule. They will always have some stereo element present, so that we can address the problem of stereo selectivity and learn in the process. How do we set, for example, this 1, 2, 3 consecutive stereo centers? How do you install C2 symmetrical moieties, and so on? So we always look for those type of heteroatom containing natural products which can be providing these challenges. Now, one can approach this problem of natural products or small molecule synthesis, if I may call them, in multiple ways. People look at these challenges from the point of view of catalysis. So you do catalytic transformations, develop strategies for making these natural products by using catalysis. There are other domains wherein you actually do target oriented synthesis, wherein you pick a complex molecule, do total synthesis of these molecules and learn along the way. One way which we thought we would approach our build-up of the chemistry when we started almost 1.5 decades back in my former employer's place, IIT Madras, was using a functional group-based approach for making these molecules. The functional group which we chose is highlighted in this red component here. And for those of you who don't know what this functional group is, let me explain to you what this red functional group is. Many people will say that this red functional group is an acrylate moiety, because you see C double bond C CO2 Me, so it is a methyl acrylate fragment. And yes, you are correct that it's an acrylate moiety. But the moment I have a heteroatom in the beta position, X can be oxygen, it can be nitrogen, it can be sulfur, what we prefer to call them as vinylogous, because a vinyl group is inserted. So vinylogous, just like your homologous series, we call these functional groups as vinylogous carbonate if X is oxygen. And you can imagine that if X is oxygen, when you have oxygen carbonyl oxygen function, it's a carbonate function basically. If it is nitrogen, then it will be NCOO, which is a carbamate function. So we will call that functional group as a vinylogous carbamate. And if X is sulfur, you can call it vinylogous thiocarbonate, and so on. Okay. So this functional group, which has a beta heteroatom substituent on the acrylate moiety, is called as vinylogous carbonate, carbamate, thiocarbonate, depending on what the nature of X is. Now, why this functional group is very interesting? Because it has all the components to behave in a completely different manner than what the functional groups are present. So when it is heteroatom on the acrylate portion, as you can imagine, because of the presence of lone pair on the heteroatom, this acrylate becomes lot less electrophilic because by the push from the heteroatom. So it still can behave like an acrylate, but not as electron deficient as acrylate. Not only that, since there is a heteroatom here and then it is conjugated with the olefin, they will behave like enamine or enol ethers. So it will combine both the propensities of these functional groups, the enol ether as well as the acrylate. And the actual reactivity is kind of a hybrid of the two, if I may call it that way. And that makes this functional group very, very interesting. Now, when we started working more than a decade ago on this particular functional group, what we found is that this is an excellent radical acceptor. The radical acceptor nature of this functional group was established in the literature through various radical cyclizations. So you can imagine that if I have a radical precursor at Y, then what I may be able to do is I can generate a radical here, and that radical can undergo a radical addition, conjugate addition, to form this CC bond, and in the process close the ring. What you get is a cyclic ring system with two stereocenters. One new stereocenter is generated in addition to whatever pre-existing stereocenter is, and this stereocenter generation can be very, very diastereoselective reaction. So this is what was known. So what is known is that these are very good radical acceptors. This is something which was there. But what was also known, that despite this being an acrylate, and acrylates, you know, are very good partners in Diels-Alder reaction. It's a textbook chemistry for you. These vinylogous carbonates are really poor dienophile. Now this one was a little bit of a surprise on the face of it, but further analysis will kind of reveal that it is not such a surprise if you really analyze it. And this was something which we identified from the literature, that they don't seem to be great dienophiles. And what was other interesting thing is, while radical chemistry is well established, their reaction under basic or Lewis acidic conditions were not developed at that point in time. Okay, and not only Diels-Alder but other cycloaddition reactions also were not well developed, nor were metal mediated transformation on this functional group were well established. So we thought that here is an opportunity to build up a program, a research program around this functional group, which will allow us to get access to the heterocyclic scaffolds by exploring chemistry, both under radical regime, which is a well-known regime at that point in time. You can ask newer questions there, and you can also ask questions in the domains where people had not asked those questions. So over the years, what we could show is that not only can you use this functional group under radical cyclization condition to make new structural scaffolds, these are called as oxa bowls or oxa cages, or natural product like scaffold, these are angularly fused triquinines. We could make these scaffolds using radical cyclization chemistry. But over the years, we also showed that this functional group can actually participate nicely in a Heck type of a reaction, for example, transition mediated reaction, which is Heck cyclization, and we can get access to isochromines, or you can get access to 1,4 heterocyclic compounds of different ring sizes. Okay, we also demonstrated that one can do a 2+1 cycloaddition. So this cycloaddition basically is nothing but cyclopropanation, and using that cyclopropanation, if it is done intramolecularly, what you will do is you will make oxygen substituted donor acceptor cyclopropane. Oxygen will be your donor, okay, whereas ester carbonyl as well as the carbonyl of this ketone are the acceptor. Or if X is nitrogen, you can also make nitrogen substituted donor acceptor cyclopropanes. And these cyclopropanes themselves are very, very reactive, and they can be used as synthon for making many target natural products. So some of the library that I showed you of the natural products which we have prepared in the first slide were actually obtained from these donor acceptor cyclopropanes. So not only that these moieties can be prepared, which are useful synthons in organic synthesis, but they can also be used for making total synthesis of natural products. What else could be done? We showed that if you tether your vinylogous carbonate with a leaving group like iodide, for example, okay, you can react it with active methylene compounds. And if you react it with active methylene compounds, you can do a simple chemistry. You can make the anion here, displace the iodide, and that iodide displacement is like an SN2 reaction. After doing intermolecular SN2, you can again generate the anion with the active methylene compound, because there are two protons, both can be deprotonated in sequence, one after another. Now, second reaction will be a Michael addition in an intramolecular fashion. In the process, what you will make is a ring-based compound. So, depending on number of carbons separating your iodide with the vinylogous carbonates, you can make tetrahydrofurans, tetrahydropyrans, and oxypane derivatives. So over the years, we actually developed this chemistry as well. But one particular part of this this functional group, which was probably most exciting and rewarding with lot of newer aspects which emerged from this study, was when we were subjecting this particular functional group under Lewis acidic conditions. When we use this functional group under Lewis acidic condition, what we could do is we could actually prepare different heterocycles. So we could prepare the N-fused heterocyclic compounds of the indole variety. We could prepare the C-fused heterocyclic derivatives with the pyran fused to them. And we could also prepare the benzofuran derivatives. Okay. And today's story is largely based on what emerged, what proved to be a question that we asked, and how it led to a newer development of chemistry. And that is what I'm going to share the story today. So when we were using these vinylogous carbonates with a strong Lewis acid like TMS triflate, and TMS triflate is one of the strongest Lewis acids that we use in the laboratory, what we could do is we could actually demonstrate that with the help of the strong Lewis acid, you can activate the carbonyl of the ester. And when you activate carbonyl of the ester, because of the push of the lone pair from the oxygen, you can actually generate an oxonium ion. And once you have generated this oxonium ion, your indole moiety can do an oxapictate-Spengler type of reaction, similar to Friedel-Crafts, if you would like to call it that way. And it will form a CC bond followed by rearomatization. Not only that, we could close the ring to make the N-fused indole derivatives, we also showed that the third position of the indole, which is more reactive, can be trapped using appropriate electrophile in the same pot to functionalize both the positions of indole, second as well as the third position of the indole can be functionalized in a single pot operation. Now again, if you look at it, this reaction development was purely on the basis of mechanistic rationale, and that is what allowed us to make the complex structure in a cascade manner, or in a what we call it as a tandem manner. Of course, if you tether this oxonium ion precursor not through the heteroatom of indole, but through the carbon, which is the second position of any heterocycle, similar kind of an oxonium ion can be generated by using a strong Lewis acid. And this time, the third position of the heterocycle will act as a nucleophile, giving us a pyran fused heterocyclic scaffold. So during this particular study, when this study was going on, when Satyanarayana and Prasad were working on this, we asked a question that these heterocycles are excellent nucleophiles, that it will work is something to be expected. But what if I replace the heterocycle, which is tethered to this oxonium ion, with a poorer nucleophile, a pi nucleophile of an alkyne? And if I can replace the alkyne as a nucleophile to trap the oxonium ion, what I would be able to do is what is called as a Prince type of alkyne Prince type of a cyclization, and that will open up newer avenues for synthesizing cyclic ethers. That was the question, that was the premise with which we started working on replacing my heteroatom with the alkyne. So that becomes a new functional group which we can think of. But of course, alkyne is there since time immemorial in organic synthesis. So we are not the first one to ask this question. Alkyne chemistry is very well established. Alkynes are precursors for cycloadditions, radicals, hydroacylations, metathesis, coupling, you name it, and then the alkyne reactions have been done. But the specific question that we were proposing was leading to this question that can alkyne participate in the Prince types reactions with the oxonium ion generated from the alkyne, from the vinylogous carbonate. And what we saw when we asked this question, and that is something which I will elaborate, is that it also participates in the hydroalkoxylation type of reaction. Okay, so these two facets of this alkyne chemistry is what I'm going to take you to. What we started with was vinylogous carbonates, but what we got into by asking certain questions was, can we use these alkynes as a nucleophile? Turned out that yes, indeed, alkynes can participate in the reaction with vinylogous carbonate, particularly if you generate an oxonium ion or an iminium ion, if X is nitrogen. Still the same type of reaction can happen, and it will generate a vinyl cation intermediate. This vinyl cation intermediate can be trapped with the counter anion of the Lewis acid or with water during workup, leading to the enol ether, which will tautomerize to the corresponding ketone. So we could show that this chemistry gives us access to a lot of tetrahydrofuran moieties, and these tetrahydrofuran moieties can also be fused with the aromatic ring. And when it is fused with the aromatic ring, what we have is a dihydrobenzofuran moiety. Okay, what if we start with vinylogous carbamate instead of carbonate? So X is nitrogen. You will be able to get access to dihydroindole through alkyne iminium ion cyclization now. So instead of even having an oxocarbenium ion or oxonium ion, you will have an iminium ion. So rest of the chemistry will be very, very similar, not identical, but very similar. And you will get access to the indolines. And if the aromatic ring is not present, you will get access to the pyrrolidines as well in a very highly diastereoselective manner. You can see that we are making in all these cases 2 new stereocenters. Starting from compound which doesn't have any stereochemistry, you get 2 new stereocenters, and to avoid steric interaction, these substituents will be trans to one another. Now, this is something which was ongoing, and this is when a student who is inquisitive brings in newer aspects, newer challenges, newer opportunities. So what he asked during this transformation was a question: what if instead of using a simple alkyne, and that simple alkyne gives me the dihydroindole or indoline derivative, trans stereochemistry, what if I tether a nucleophile, let's say a hydroxy group, onto the alkyne? Now, if the same type of chemistry were to work out, what I should be able to do, his premise was, Prasad was the name of the student, he said that this carbocation intermediate should be trapped by this nucleophilic hydroxy group. And if I can trap that, I will get one more ring. And when he came up, he suggested that these are the aspects, these are the products which I think would form. And to me, looked like a very, very rational mechanistic design. And for that, I suggested that we go ahead and attempt this. When he went to the lab and attempted, what he found is that whatever was originally thought did not happen. But he was patient and tried to find out what actually did take place. After analysis of the products, what he figured out is that you do not get this 5-membered indoline type of derivative, but what he got is a dihydroquinoline type of a derivative. Okay, and he quickly established that yes, this is indeed what is happening by taking different precursor alcohols, and he showed that this reaction is quite general, giving him access to the dihydroquinolines, which are also fused with the pyran moiety. Okay, and not only that, it could be also fused with the oxypane moiety. These products were obtained. So this reaction is general. But how does this reaction happen? We anticipated that the reaction should give us product like this, but what we get is a different type of a product. So obviously a synthetic chemist will try to rationalize the outcome of the reaction. So we wrote a mechanism. The working hypothesis was that maybe what is happening here is before even you activate your nitrogen with the Lewis acid seems to be activating your alkyne. And if alkyne gets activated and hydroxy group does hydroalkoxylation of the alkyne in the presence of strong Lewis acid, Okay, what you will end up getting is an enol ether. Now, what was known at that point in literature is catalysts like gold can do this, platinum can do this, but not so much the strong Lewis acids. That one was something which was not that well understood. That even Lewis acids can actually generate the Bronsted acid in situ, and they will generate these kind of intermediates in transiently, which can give unique reactivity. Now, what happens? The Lewis acid will activate your ester, giving me the iminium, much like the earlier case. But enol ether will act as a nucleophile on the iminium ion, not the alkyne anymore, because alkyne got converted into enol ether before even iminium ion was formed. And then you trap that iminium ion with enol ether. In the process, generate an oxonium ion, and this oxonium ion will lose a proton from the alpha position, generating the double bond, giving me the pyran ring, which is fused with the dihydroquinoline ring. That was our working hypothesis. This is what we thought could be happening. Now, when you think of a mechanism, you try to support your mechanism by carrying out some experiment. Prasad also was no different. He thought that, why don't I do this particular transformation? Try to trap my intermediate oxonium ion by doing something which will kind of give credence to the mechanistic hypothesis which we have. So he trapped that oxonium ion with trithylsilane kind of a nucleophile. Okay, and that silane, essentially the hydride will be the nucleophile which will trap the oxonium ion, and that will lead to the formation of the tetrahydropyran type of a moiety here, kind of giving credence to the fact that yes, oxonium ion indeed is possible. And it is at this point in time that Santosh Nanda, who was coming from Orissa, along with Dharmendra, they were looking at this mechanism, and they asked the question that, can we trap that oxonium with silane? Answer is yes. But is it necessary for you to have the iminium ion for making that oxonium ion? Very, very valid question. Can that happen without iminium ion? My question was, why do you guys want to do this? Their answer was, sir, if we are able to trap that oxonium without iminium ion, this could be one of the fastest way to get access to the cyclic ethers. How? How so? This way. You have an oxonium ion, you can trap with nucleophile, let's say silane, you will get a cyclic ether. There is no iminium ion further from there. How do you get oxonium ion? Starting from the alkynyl alcohols. Okay, so if you have alkynyl alcohols, alkynols, you should be able to convert that into the enol ether or an oxonium ion in situ, and that oxonium ion can be trapped with different nucleophile. You will be able to get access to the cyclic ether. And alkynols are rather readily prepared. For example, if you take an epoxide which is available on the benchtop, open it with the phenylacetylene derivative, you will open in one step, you make alkynol. In the second step, you will install the cyclic ether. So that idea was very, very interesting, and I suggested to both these guys that you please go ahead and do that. So they went ahead, tried this reaction, and sure enough, what they found is that they use silane as a nucleophile in the presence of Lewis acid. Stoichiometric amount was required for effecting this transformation. Sure enough, they got 78% yield of the tetrahydrofuran derivative, 2,5-disubstituted tetrahydrofuran moiety. Only thing is diastereoselectivity was not that great. But nevertheless, we went ahead and then quickly prepared these substrates, the alkynols, and subjected them to optimized reaction condition, which involved the formation of a 5-endo dig. So you can see this hydroxy group is cyclizing here, and since this particular carbon is sp carbon, we call it 5-endo dig hydroalkoxylation, because hydrogen and oxygen both are adding, followed by the reduction of the oxonium ion. So this cascade, which involved hydroalkoxylation and reduction, was used for the synthesis of these tetrahydrofuran derivatives. One drawback of our reaction, while the yields were fairly good in majority of the cases, one drawback was the diastereoselectivity. You will see that only about 3:2 or 1.5:1 was what we observed. The cis isomer was the major isomer. We of course confirm it by NOE studies and all. Trans isomer is the minor isomer, and again we have full characterization of these. Majority of the cases yields were good, except when you had an electron withdrawing nitro group on the aryl ring here. So aryl group should not have electron withdrawing group. Then the reaction does not seem to work, and that is to be understood because mechanistically this position will generate a vinyl cation, and when aryl ring has an electron withdrawing group, that vinyl cation will be destabilized, and hence the reaction does not happen that readily in the nitro case. But other cases we got a fairly good yield. We could also make spirocyclic cyclic ether, so that was something which was quite interesting. As is our custom, we normally apply our method in total synthesis. So two natural products were prepared using our method by taking appropriately substituted alkynols, and those two natural products, calixoline A and B, were both prepared as a mixture of diastereomers. Could be separated, but we could characterize them fully as 3:2 diastereomers in fairly good yield. The only time we got very high diastereoselectivity is when we had a ring associated with the alkynol, and that conformational constraint is what was responsible for giving us very high diastereoselectivity. Now we saw that tetrahydrofuran can be made. Can we prepare the 6-membered rings using this? So we prepared the substrates. Dharmendra and Santosh, they both went ahead, prepared the substrate. Sure enough, they found that the hydroalkoxylation, now this time it is the 6-endodic. Okay, this is where your proton will be going eventually, and that will become 6-endodic hydroalkoxylation followed by reduction using silane, and that again will give me the cis isomer as the major isomer. Not only the yields were good, but also the diastereoselectivity of this transformation was excellent. We get essentially only the cis isomer in majority of these cases. Okay, again what we found that if you have a nitro group, the reaction does not work. Otherwise, in general, the reaction works fairly well, giving the corresponding products in very high diastereoselectivity. Okay, in general. What was also interesting is, even if I have another alkyne in the molecule, okay, only the alkyne which is internal alkyne, which will have aryl substituent, that is the one which will participate in the endodic hydroalkoxylation preferentially. So reaction gives me selectivity for hydroalkoxylation with the aryl alkynes, not the terminal alkynes, when both are present. Okay. Not only that, even olefins can be tolerated in this particular transformation. So we saw that the reaction is able to discriminate between alkynes of different type and also alkyne versus olefin, giving me only alkyne based reactivity for this particular transformation. So this particular aspect was very, very interesting. Now, obviously, when we see this kind of a thing, we want to ask a question, will the reaction work for a 7-membered ring as well? So we thought, why don't we make 1,4 heterocycles, because that is one of the interests which we have, making 1,4 heterocycles. So these alkynols which are having nitrogen in them were readily prepared from amino acids. So you take amino acids, reduce them to aminols, protect nitrogen, do propargylation, Sonogashira, and then you will do the hydroalkoxylation reduction cascade to install 7-membered rings. Again, the yields are fairly good. The diastereoselectivity in majority of the cases is following the same trend that we observed in the case of a 6-membered ring. Right? So one could make 2 7 disubstituted derivatives. One could make also 2 6 disubstituted derivatives as well. These are 1,4 oxazepine derivatives. They are having heterocycles with 2 heteroatoms. So we showed that reaction works for 5-membered ring, 6-membered ring, 7-membered ring. We asked a question that we know that the hydroxy group can selectively react with only alkyne having an aryl ring, doesn't react with olefin, doesn't react with alkyne. So what we asked is, do we have to have silane externally? Can these olefins and alkyne react as nucleophile in situ to trap those oxonium? If that was to happen, what you will get is a bicyclic Pyran system, and indeed this reaction does happen. You are able to make the bicyclic Pyran systems by generation of a vinyl cation in the case of alkyne, and that vinyl cation can be trapped with the counteranion of the Lewis acid, which is TMS triflate, and you will get vinyl triflate as the product. And as you can appreciate that these enol triflates are good partners for further coupling chemistry, and that is something which we are trying to use for making more elaborate systems using this particular chemistry. One aspect was, do we have to have then only silane as a nucleophile? From the previous example, we know that alkynes themselves, when they are present intramolecularly, can act as a nucleophile. Olefins can act as a nucleophile. So we figured that instead of silane, if you use TMS cyanide, so nitrile can act as a nucleophile. And instead of having secondary ethers, what you can make is you can make tertiary ethers at that particular position by trapping the oxonium ion, this time with a cyanide rather than the silane. So again, the reaction was fairly decent yielding, and selectivity was also fairly all right for installing the tertiary ethers. Now, those of you who know a little bit about cyclic ether will appreciate this chemistry, because making tertiary ether using conventional Williamson's etherification is always fraught with challenges, whereas our method allows you for formation of tertiary ethers without any difficulty. Okay, so this is a very useful method for making tertiary ethers. Now, again, to apply our method for synthesis of natural products, we targeted another natural product called centrolobene. It's a very popular target. If you search the literature, you will find that centrolobene is a tetrahydropyran derivative, and maybe 40 synthesis of this molecule must be there, because anybody and everybody who develops a method for synthesis of tetrahydropyran, particularly the cis isomer of tetrahydropyran, want to test their strategy on the synthesis of centrolobene. So our synthesis, I can say, not only gives access to the centrolobene itself, but it also gives access to the homologue of centrolobene. How do you get homologue? We know that the alkyne can be tolerated in our reaction. So we prepared substrates in which either 1 or 2 carbons were separating the alkyne on this tetrahydropyran. This tetrahydropyran was prepared using the hydroalkoxylation reduction cascade. And at the end of the reaction, we take this derivative, do a Sonogashira coupling with idophenol, and then reduce the alkyne by hydrogenation. That way we will get access to the centrolobene natural product. Of course, one problem was that diastereoselectivity when n is equal to 0 was not that great. So to circumvent that problem, we explored the alternate path, wherein we open this epoxide with propargyl grignard to make the alkynol. Sonogashira coupling with appropriate aryl iodide, which will be having paramethoxy substituent on the aryl ring, gave us the alkynol precursor, which was the substrate for our cascade hydroalkoxylation reduction reaction. We get this particular tetrahydropyran with very high diastereoselectivity, and then you deprotect the benzyl group of this particular pyran to make the natural product centrolobene. So what we showcased is that indeed our method can be used for making natural products, not only 5-membered, but we can also make 6-membered pyran based natural products using the method that we have developed. Okay, so next question naturally was Dharmendra asked is, oxygen works, will nitrogen work? If nitrogen works, what would happen? You will do hydroamination now, the endo-dig hydroamination followed by reduction of the iminium ion this time, and you should be able to access the nitrogen heterocycles. So a substrate was prepared very quickly again. This one is not as straightforward synthesis for substrate preparation as is the case with the oxygen, but for other substrates we could make it quickly by opening the aziridines, at least in few cases. So it mirrors your oxygen heterocycle synthesis. Nevertheless, you can convert the homopropargyl alcohol to the corresponding tosylate and displace that tosylate with the tosylamine to make the nitrogen precursor. Once you have N-tosyl protected alkynyl amine, you can actually do reductive etherification and convert this alkynyl amine by endo-dig cyclization into the pyrrolidine derivative, again with very good yield. So when you go to nitrogen, one thing you want to know is what are the protections on nitrogen are tolerated. So what we did is we prepared substrates where there will be different protecting groups on the nitrogen. So you can see different protections on the nitrogen were studied to understand the scope and limitation. We already know the tosyl group works, but what about other sulfonyl? So we used ortho nitrosulfonyl and paranitrosulfonyl, orthonosyl, paranosyl. They both work, but DR is not that great. When you have methyl group, methane sulfonyl group, the DR is also good, yield is also good. If you use triflate, the yields are okay, but diastereoselectivity is not good. If you use trifluoroacetamide group, CF3CO group, your yield is moderate, reactivity drops because a lot of starting material is recovered unreacted. Your DR also is not that great. And carbamate protection like BOG and CBZ simply fail to react in this transformation, clearly suggesting that you have to have certain acidity of this NH proton for it to react in this under the conditions which we have developed. Okay, so hydroamination followed by reduction cascade works well when N is sulfonyl protection. So what we did is we decided to go ahead with the tosyl protection because that is the most common one. We do the 5-endo-dig hydroamination reduction cascade, and we are able to make this kind of pyrrolidine derivatives in a highly selective manner. What was interesting in these cases, and I want you to pay attention here, the diastereoselectivity in all these 5-membered ring formations, you will see, was uniformly excellent. It was uniformly excellent. That you always got only the cis isomer of the product exclusively almost. Now compare this with the oxygen variant, where for 5-membered ring formation, our diastereoselectivity was moderate at best. We got only about 3:2 or 1.5:1 for favoring cis isomer. Here we got cis isomer, but almost exclusively. So nitrogen, while mirrors reactivity, selectivity is slightly different, which is much better than what we observed for the oxygen cases. Okay, so fairly general reaction, very quick way of making the pyrrolidine based systems. We of course confirmed the stereochemistry by taking X-ray diffraction studies on one of the derivatives. You can extrapolate this study to the 6-membered derivative. So 6-endo-dig hydroamination reduction cascade is indeed possible, and you can get the piperidine derivatives this time with a very high selectivity. Again, you will see that diastereoselectivity, while it is good, it is not as good as what we observed for 6-membered ring formation with oxygen. So hydroamination reduction cascade still gives good DR, but not as good for 6-membered ring. So you see that distinct difference is there between oxygen and nitrogen. And again, we got the crystal structure to confirm the cis stereochemistry of the products in couple of derivatives.
Sir, sorry to interrupt. Sir, sorry to interrupt. Maybe some technical error. Your slide is not actually coming. So,
oh, okay. So should I escape and then try again?
Yeah, please, sir.
Is screen visible now?
I mean, you are visible, but
okay. Maybe I will log out and log back in.
No, not. I mean, stop presenting, then
okay.
Just start presenting again. Yeah.
So presentation has stopped now.
Yeah, I mean it's not.
Tell me when it is visible.
Yes, sir, it is visible.
Okay, great. Sorry about that. So from this slide only it was not visible, right? Or okay, so now it's visible, right?
Yes, sir, it is visible. Please go ahead.
Good. Yeah. So 6-membered rings, we saw that diastereoselectivity is comparable, is good, but not as good as the pyran cases. Okay, so nitrogen does give different reactivity, particularly because of the presence of the tosyl group. Of course, we confirmed the stereochemistry as cis by doing single crystal diffraction studies on one of the derivatives, and of course we record NOEs in many of these cases, most of these cases I should say, to confirm the stereochemistry. One interesting observation what we made is, if I have a strongly electron releasing group, either paramethoxyphenyl or the thiophene type of group, the reaction stops at giving us giving us enamine. The further reduction does not happen. In fact, this isolation of these enamines also gives credence to the mechanism that we talk about. And indeed, what we found is that these derivatives come in handy at a later point if you want to do the functionalization of the compounds. Okay. Will the other nucleophile work other than silane? Yes, indeed. TMS cyanide does give you access to that. And as is the case, we always try to functionalize our molecules. So the enamine, for example, can be subjected to the hydroboration oxidation so that you can install the 3-hydroxypiperidine derivatives. And when we tried doing the reduction of this, what we seem to be getting is the ring-contracted product, which is interesting in itself. We of course use this method for synthesis of natural product. For example, one molecule which we had prepared, we deprotect the nosyl group and then open the epoxide styrene oxide using the nitrogen nucleophile. And once we get this aminol, we do the Friedel-Crafts type of a reaction using polyphosphoric acid in situ to get the MCN4612Z, which is a natural product prepared using our strategy, what we have done. So you will see this theme acting whenever there is a method. If there is a possibility of natural product, we want to use it. Now that we have discussed that nitrogen and oxygen can form reductively, this endodig, 5-endodig reductive hydroalkoxylation cascade can be done. We became a little bit ambitious and we said, is it necessary that we have to have only one heteroatom? What if both heteroatoms are there? So we said, what if we have the hydroxylamine derivative which is tethered to an alkyne? And if we do this reductive reaction, what you should get is you should be able to make the isoxazolidine derivatives using this same method. And turns out, yes, indeed, that this reaction works quite well. Your diastereoselectivity is somewhat moderate, but this is to be expected because 5-membered rings typically gave us poor diastereoselectivity for oxygen case. And what we are doing here is a hydroalkoxylation cascade. So the diastereoselectivity is not that great. But yields are fairly good in majority of these cases, giving us access to now 1,2 heterocycles, which are 5-membered ring. Why we are interested in 1,4 heterocycles of this type? One is these moieties are present in many biologically active molecules, but they also give us access to making these isoxazolidine derivative in an enantiomerically enriched form. So what we do is, for that, we prepare the propargylic alcohol in an enantiomerically enriched fashion following Carrera's protocol. This is Carrera's protocol. And then do the Mitsunobu of this propargyl alcohol with the hydroxylamine which is protected to invert the stereochemistry at this center and also install the hydroxylamine. And then you do reductive cyclization. You will be able to set both these stereo centers with not only very high diastereoselectivity, but also with very high enantiomeric excesses. Okay, so that is something which we are taking it further. Other interesting aspect of these 5-membered 1,2 heterocycles is that the NO bond is weak and can be cleaved with appropriate reagent. For example, if I cleave the NO bond with zinc, what I get is access to 1,3 amino alcohols. Now these are the motifs which are very interesting, and the hydroxylamine reductive vitrification gives us the access to 1,3 hydroxylamine, which again can be used in the total synthesis of these type of natural products. And that is something which is ongoing chemistry right now. We have made these amino alcohols, we have done the metathesis, hydrogenation. Now we just need to do the deprotection to complete the total synthesis of this norcellosedamine natural product using the homegrown method. Okay, so now what I let me quickly summarize what all things I showed you up until now. What I showed you is that you can have an oxonium and iminium, and alkyne can trap that to generate a vinyl cation, and you can trap that vinyl cation with a nucleophile to make the cyclic ether or amine. But if your nucleophile is tethered already to the alkyne, you get a different reactivity, wherein alkyne reacts first, then the iminium, for example, is trapped by the new nucleophile enol ether, and you get a product of this type. So when we were developing this chemistry, that time Santosh asked the question, what will happen if you tether nucleophile not to the alkyne, but tether nucleophile to your precursor of electrophile? What do I mean by that? Instead of using aldehyde to make oxonium ion, what if you use salicylaldehyde to make the oxonium ion? So aldehyde will have a hydroxy group. So this hydroxy group will act as a nucleophile. This aldehyde will be acting as the precursor for formation of oxonium ion. So one possibility is you will form an oxonium ion, alkyne will trap that, and the hydroxy group will trap it. Okay, this is one possibility. But we also know that in these type of substrate, the alcohol directly may first react with the alkyne, generate an enol ether, and this enol ether may actually react with salicylaldehyde in the subsequent stage, and you will end up getting compound of this type. Now, which of these two is the one which will form? That was the question. What we figured, it would not matter, because both the motifs, whether path is followed one on the left side or path is followed on the right side, both give us natural products. Okay, the skeletons of natural products. So we thought best way to find out is go ahead and do a reaction. And when you actually do the reaction, sure enough, what we observe is out of the two possibilities, one path on the left, one path on the right, the hydroalkoxylation first or oxonium ion formation first. Which one will dominate? It turns out that it is the right path is the right one. That is, you first do hydroalkoxylation of the alkyne, and then that enol ether is the one which will react, giving us access to the chromine ketals. Again, this reaction was fairly general. We could make 5-membered ring fused with the 6-membered chromine acetals could be prepared in excellent yield in majority of the cases. Not only 5-membered ring fused, you can also get 6-membered ring fused derivatives by having an alkyne which is having now extra carbons for separation of the hydroxy and alkyne. Then you will be able to get access to again the chromine ketals, and reaction again is quite general with excellent yields in majority of these cases. Basically, what happened if we do not have a substituent on the alkyne here? If we do not have substituent on the alkyne, what happens actually is, instead of giving you the 6 endo-dig reaction, you get 6 exo-dig reaction, and that leads to the spiroketal formation rather than giving the spiroketal through the endo-dig transformation. Now, the only thing we have changed is that we have replaced alkyne with hydrogen rather than aryl ring, and you can make spirocyclic ketal derivatives again in excellent yield in majority of these particular cases. So if you understand the mechanism of these transformations, you will be able to use this chemistry to make lot of cyclic ether containing systems. Now, in the last, Sahu, how much time do I have?
Sir, we can go ahead maybe with 10 or 15 minutes, 15 minutes more.
Okay, fine. Then I don't have to skip anything. I will complete the story. Just like 5 and 6 membered rings can be made, we asked the question, can this method be useful for making larger rings? Turned out in the literature, making larger rings by hydroalkoxylation, while it is described, it was fraught with challenges. What were the challenges? For example, Schreiber said that you can do 7 exo-dig or 8 endo-dig cyclization to make either a 7-membered ring or a 8-membered ring using gold catalyzed reactions with alkynols. But as you would realize that, this alkyne is conjugated with the carbonyl group, and that is what will make the reaction selective one way or the other. Viken also showed that, you can do similar type of reaction primarily in an endo-dig manner, but again, the selectivity is dictated by presence of this carbonyl in this reaction. Ley showed that one can use platinum catalyzed reaction, and if you have a diol tethered to an alkyne, you can get access to again 8 endo-dig or 7 exo-dig. Both type of reactivity is available. Problem there is that most of these reactions suffer from very poor regioselectivity issues, and more often than not, you get a mixture of products. So while some progress has been made on synthesis of these, the exclusive formation of one product over the other is not there, and you have to use expensive precious metals, platinum, gold, silver, combination of those. Okay, so we wanted to ask this question: can our method be useful for making larger rings? So we went ahead and prepared substrates. So for example, you prepare nitrogen tethered alkynol, okay, and ask this question: what will happen if I react it with salicylaldehyde? Will I get a 7-membered fused with a 6-membered ring? Turns out, yes, indeed, not only that you get it, but you get it with excellent distereoselectivity in majority of the cases. It's a fairly general reaction. You can get a 7-membered ring fused with a 6-membered ring. Okay, not only that, you don't have to have tocile protection, you can also have tertiary amine, and all these products are going to be enantiomerically enriched because they were prepared from corresponding amino acids, and that's where they become very, very valuable products, so to speak, and very rapidly these can be assembled. Complex structures can be made very rapidly with complete regioselectivity. Again, we find that you can have different tethers. It's not necessary that I always have to have nitrogen here. I can also have oxygen. So I can make dioxa derivatives. So you can have both as oxygens. You can also have sulfur and oxygen combination. Okay. So 1,4 heterocycles, OO, NO, and SO, you name it, we will be able to make it using this kind of a strategy. So fairly general method for making 1,4 heterocycles, which involves 7 endo-dig hydroalkoxylation followed by formal 4+2 cycloaddition. Exclusive formation of 7-membered rings. What about 8-membered rings? You add one more carbon separating between the alkynol, and sure enough, you can get 8-membered ring which is fused with a 6-membered ring now. Again, the regioselectivity is complete. Stereoselectivity is also excellent in majority of these cases. Okay, most of the cases you get only one particular diastereomer of this particular product. So very, very robust reaction. You can make NO, you can have SO, both type of heterocycles can be made, which will be having 8-membered ring. Now this is one of the earliest examples which is giving complete regioselectivity for 8-membered ring formation. Then we became ambitious. What will happen if I want to make 9-membered ring? Is it possible? Answer is yes, indeed. 9-membered ring also is possible. You can make 9-membered rings fused with a chromine derivative, and again reactions work in a slightly diminished yield, but only marginally diminished. It's not like 9-membered ring formation is further challenging, but yet we are able to make it using our method and with complete regio control. And that is something which was very, very satisfying, that we don't have to use precious metals, but yet we are able to achieve complete regioselectivity, very high diastereoselectivity for formation of these products. So this chemistry became so general that we could make cyclic ether fused derivatives of this type, wherein you will see that I will have a 6-membered ring fused with an 8-membered ring, which is fused with another 6-membered ring. These are the type of motifs you will see. Variation of these are present in polycyclic ethers. You can make C2 symmetric derivatives. For example, if I have two alkynols, one hydroxy group will cyclize on one side, the other hydroxy group will cyclize on the other side, and you can make C2 symmetrical 6, 7, 7, 6 kind of fragments using this chemistry. One interesting reaction that Santosh explored was using the product. For example, we had these allylic sulfides. So what he did is he subjected to the carbene precursor so that you can react sulfur's lone pair with the extrusion of nitrogen. You can make a yellide, and that yellide will undergo 2,3 sigmatopic shift to make these bridged bicyclic scaffolds. So this was a very interesting outcome of one of the products that we could actually do ring expansion and make bridge systems in the process. Okay, so let me in the last few minutes let me quickly summarize what we have done in the non-radical regime of late. I explained to you that in the past we had used radical cyclization chemistry on vinylogous carbonate for making the angularly fused system. So idea is you have this iodide, you can generate radical here, that radical will cyclize onto this olefin, giving 5 exoteric cyclization. The new radical will do another 5 exoteric cyclization, giving me angularly fused triquinone derivative. So you will make a 5-membered ring fused with a 5-member ring, fused with a 5-member ring. It's called angular triquinone. Okay. We extrapolated this reaction wherein we showed that you can make a radical precursor from alkyne. So for example, if you take thiophenol, react it with AIBN, you will generate a sulfur radical, and that sulfur radical will cyclize onto the alkyne, okay, and the new radical generated, that will cyclize onto the indole portion. So you will get N-fused indole derivatives, and depending on what my R2 and R3 are, this was a very interesting observation we had made, that rather than getting the indolene derivative, you may end up getting actually the indole derivatives as well. Okay, so based on this chemistry, pardon me, that we had developed, we asked the question, what will happen if we use alkyne together with wine-analogous carbonate and carbonate? What will be the outcome of the reaction? So the question really is, what if alkyne is tethered to wine-analogous carbonate and I do the reaction under radical condition? Now, will I be able to make dihydrofuran derivative of this type if right X is used? What is the best way to find out this answer? The best way is to carry out an experiment. So Padmaja came along in the group around that time, who asked this question and carried out the reaction. So what she found along with Prasad is that if you subject these alkynyl wine-analogous carbonate to the reaction with tributyl tin hydride AIBN, standard radical condition, you actually do end up getting dihydrofurans as derivatives. Again, the diestereoselectivity was only moderate in many cases, but the yields were excellent in majority of the cases. Okay, so this became a very quick way of assembling dihydrofurans. Now you won't find many methods for making dihydrofurans in the literature which has a tetra substituted. So this method was particularly interesting for making tetra substituted dihydrofuran derivatives. Now one question which we wanted to ask is, what if I don't use tin hydride, but if I use thiophenol again, then what will happen? Will I get sulfur substituted dihydrofuran derivative? Because that will be the vinyl sulfide, which will have its own chemistry. So we attempted the reaction. What we find when we use thiophenol instead of tin hydride, we find that rather than getting dihydrofuran, we end up getting furan. This was very interesting. How is it that instead of getting dihydrofuran, we get furan? But before we answer that question, we checked whether reaction is general or one-off. So it turned out reaction is quite general. It works with variety of substrates. You can have different type of aryl ring on my alkyne. So you can have simple phenyl. You can have electron withdrawing group substituted phenyl. You can have heterocyclic alkynyl derivatives as well. You can have indole derivatives. You can have thiophene, benzothiophene derivative. Reaction works uniformly well, giving me access to the furan derivatives, which is a tetra substituted furan. Again, if you see the literature, while there are many methods which will give you access to furan, the real challenge in furan synthesis is putting the substituents where you want. And from that angle, this method becomes particularly useful. One of the very few methods which can give you tetra substituted furan very rapidly using radical chemistry particularly. Okay, so this is a fairly general reaction. Not only that, you can have different substituent at R2, you can have different substituent at R1, but you can also use different thiols if you would like. For example, you can use naphthyl thiol, you can use paramethoxy substituted thiophenol, you can also have pentafluorothiophενol. And in all these cases, the reaction does work, giving you corresponding furan derivatives as well. You don't have to have necessarily the electron withdrawing group as wine-analogous carbonate. You can also have wine-analogous ester, at which point you will get essentially the ketone functionality rather than ester. And why that? You can completely take away the electron withdrawing group altogether, and you can simply get the methyl substituted derivative if you use simple enol ether for carrying out this particular transformation. Okay, so reaction is very, very general, and it gives access to the tetra substituted furan. We tried to understand the reaction mechanism. So what we did is we stopped the reaction early while using thiophenol and AIBN, and sure enough, what we observed is formation of a dihydrofuran intermediate. And when we subject this dihydrofuran intermediate again to the reaction condition, what we end up getting is that dihydrofuran gets converted into the furan derivative. So based on this, what we propose, the mechanism of reaction is, first your radical adds to the alkyne, that alkyne generates a new radical, that alkyne radical will add to analogous carbonate, giving the dihydrofuran derivative after reduction. Now the dihydrofuran derivative reacts with thiol radical to generate a new allylic radical. You can see there is a radical here, and that allylic radical will lose hydrogen with excess thiophenyl radical to generate the furan. So this is very interesting that under the reduction condition of using thiophenol, you actually end up getting oxidized product in the process. So that way, it's a very, very interesting mechanism that we thought is operative in this particular transformation. Now, last 1 minute, what I would tell you is, when one of the derivative that we were using had this naphthyl ring as alkyne substituent, and what we ended up getting is, we did get the expected furan derivative, but in addition to the furan, we also ended up getting the radical which was here underwent cyclization with the adjacent naphthyl ring, generating a 5, 6 and then 6, 6 cysteine ring cysteine, naphthyl group fused cysteine. And these two products were separated after doing reduction with lithium aluminum hydride, and this alcohol was separated from that alcohol. What was interesting in this particular product was that this product displayed atropisomerism. What is atropisomerism? Free rotation across the CC bond between the two aryl rings was restricted. So we designed a substrate. We said that what if we have this dialkyne, two analogous carbonate, two alkyne subjected to reaction condition, will we get this kind of a product? And if we get this kind of a product, it should display atrop selectivity, because there are 1 and 2 substituents on one furan ring, and same 1 and second substituent on the other furan ring. So just like biphenyl, will they show atrop selectivity, atropisomerism? Indeed, reaction did give us the product which was atrop selective, and in the NMR spectrum we can see that there is a AB quartet which is corresponding to these hydrogens. Okay, so that was a clear-cut sign. How do we confirm that further unambiguously? You simply put a thiophene ring separating the two, and you get this product. And in the product which is separated by thiophene, where there won't be any restricted rotation, you will see that same protons, both these will appear like a singlet, not the AB quartet as you would expect here. Okay, so clearly these were the first examples of atropisomeric bisfuran derivative. So very, very interesting chemistry. We could iterate this to install one furan after another. So you start with the furan which you made using our strategy, convert that ester to the aldehyde through 2 steps, make propargyl alcohol, add the hydroxy group to diethyl propiolate, make analogous carbonate, and repeat the reaction. So you install one additional furan. So you can keep repeating and keep adding. Every 4th step you will add one more furan ring on the motif. So it can be iterated to add more furan rings, and effectively you can also derivatize these, because for example here you have this vinyl stannine, you can do Stille coupling to make more decorated furan. Or if you are interested, you can take the furan, hydrolyze the ester to the carboxylic acid, and carboxylic acid can react with this phenyl ring to do via Friedel-Crafts reaction to make now benzofuran derivatives or naphthofuran derivatives precisely, to make more elaborate structures in the process. Okay, so to sum up, what I have shown you today is that you can take alkynols, alkynyl amines, and you can develop chemistry around it, either under Lewis acidic condition or also under radical condition, to make variety of scaffolds. Okay, what is required is, if you understand the mechanism of the reaction, ask a question and carry out the experiment, you will be able to do a lot of complex chemistry in a very, very simplistic manner. Not only that, if you are brave enough to be prepared for taking surprises along the way, analyze those surprises, take those challenges as opportunities, then you will be able to solve some fantastic problems along the way in your research. So that's the take-home message for me to all of you. This is the summary of the entire lecture. Of course, all this is not possible without dedicated bunch of students, and I have a very dedicated bunch of students. So their names are listed here. Their names were there on the slides as well. The one which are highlighted in red are the ones whose work I have talked about. The one in black, those whose names are in black, I have not talked about their work. Of course, I have collaborators. I did not touch upon their work as well. So, but that funding, without money, you cannot do anything. So, thankfully, group is well funded through CSIR, BRNS, ACRB, and of course, IIT Bombay also supports us in many ways in terms of instrumentation and so on. So, let me leave you with a somewhat older picture of the group. A lot of things have changed now because this was a pre-COVID picture. Now post-COVID, a lot of these students have graduated, gone on to take up their next assignments, and new students have joined. But as you would appreciate, the times that we are in can't really take a group picture with masks off. So I will leave you with this particular picture. Thank you for patient listening, and thank you, Sahu, for this kind invitation and allowing me to share chemistry with your students here. Thank you. I'll be happy to take questions if there are any. Are there any questions?
Now the talk is open for discussion. So there are some questions in the chat box. What is where endotrig and exotrig will be favored?
Okay. So let me show you that particular slide where we had this endo versus exo. It's a very pertinent question. Okay, let me show you here. Is it visible? So you can see,
yeah, it is there.
Whenever we have this R group, whenever you have this R group, if the R group is such that it stabilizes the vinyl cation generated at this position, then the hydroxy group attacking to in endo fashion is preferred. When this R group is hydrogen, for example, between the alkyl group, the vinyl group formation at this carbon will be somewhat better compared to when the hydrogen is present. And that's when these type of substrates, what we observed, they undergo 5 or 6 exodig hydroalkoxylation. Whereas whenever there is a group, R group, which is stabilizing the vinyl cation, that time it will follow the endodig path. Is that clear?
Okay, sir. This was a question from one of our old students.
Sure.
It was in the chat box.
Sure, no problem.
The second question is, how is it to characterize these compounds? Whatever the compounds which you have shown. This is a question from one of our students also.
Okay.
How easy it is to characterize this compound? Yeah.
Okay. So with little bit of experience, these compounds can be easily characterized. And when I say easy, you have to keep in mind that you have to know a little bit of NMR and things like that. One thing which I insist in my group is that getting proton carbon IR mass spec is a standard that you have to have. But in addition to that, to ascertain the stereochemical outcome of the reaction, for example, here you will see that there are stereo centers, right? So majority of the time we look for the NOE experiments. So for example, if I were to show something relatively simple, right? Let me take you to the oxygen example. Yeah, here. So if you see here, in these cases, you can ascertain the stereochemistry by the NOE experiment. So if you look at the hydrogen here and hydrogen here, when you irradiate one hydrogen, you will see enhancement in the intensity of the other proton, and when you irradiate this proton, you will see enhancement in the intensity of that proton. So the NOE experiments, 2D NMRs, a lot of those experiments we have to do for assigning the stereochemistry and overall structure. Wherever possible, we try to crystallize the compound. If they don't crystallize, we make derivatives of that so that you get solid compounds, and try to do single crystal diffraction for unambiguous structural assignment. So a lot of effort goes in that, in the assignment of the stereochemistry, assignment of the structure overall. But with little bit of experience, these become relatively easy, I must say that. So most of these students like Santosh Nanda, for example, or Dharmendra, and these people, if you interact with them, you will find that they became quite good with interpretation of these two-dimensional NMRs and so on. That becomes a requirement essentially for the work of this type.
So these are the questions in the chat box. So any more questions from the participants? Okay. So you can, if you have any question, you can directly interact with Professor Ghadpure.
I'll be happy to answer.
So I have one question. I mean, how easy to get? Sure. I mean, do you get single crystal for all of your compounds? I mean, XRD structure like crystals for compounds?
I think it's a very good question. We were lucky. In fact, if you go back to even Chennai days and even today, I think apart from some inorganic chemist, our group generally is one of the ones who have maximum crystals. Okay, I think organic chemistry wise, if you see, I think we will probably have maximum crystals in our department probably. One reason for that is that I insist that we get as many structural confirmations as possible. That is one reason. Because you can see, for example, here, see there are 3 stereo centers. Even though we have done NOE and extensive studies on that, when the compound crystallizes, and that happens when you have these kind of docile kind of groups more often than not, then I don't see a reason why we should not take a crystal structure. We have access to the machine, and that gives me unambiguous stereochemical assignment, which helps me in learning the NOEs further. Okay, so we end up doing that. So barring 1 or 2 projects, for example, Furan project, the last one that I discussed, we didn't get many crystals there. Maybe 1 crystal structure was there probably, but there are many projects where you see routinely 5-6 different type of crystal structures will be there. So and if they don't crystallize, we derivatize them. So whenever the product does not crystallize, we actually convert them into species which will crystallize. For example, in these kind of cases, you have this ester, so you can reduce the ester to alcohol, and that alcohol you convert it into 3,5-dinitro benzoate derivative or para-bromobenzoate derivative, and you can crystallize the product and then get a crystal structure. So we do try our best to get crystal structures wherever possible. I mean, despite doing all the NOE and the correlation studies, we do get crystal, we do go ahead and then record it. This is learning, right? I mean, you learn a lot by doing that anyway.
Okay, sir. Okay. So, is there any more questions from the audience? So many of your students are listening to you.
Yeah, possible.
So if there are no more questions, so let us thank Professor Ghadpure for his wonderful talk.
Thank you.
I hope that the participants must have enjoyed the talk and take some message home. Thank you, sir, for being with us.
Thank you.
Really a nice moment to have you Yeah. Thank you very much, sir.
Thank you. Thank you. Thank you very much. Good to see you after a long time.
Yes, yes. Okay. Okay. Thank you,
Okay.
sir.
Okay. Thank you. So I'll log out now.
Okay.
Yeah.
Yes, sir.
Thank
You can
you.
log out. Okay,
Yeah.
sir. Thank you.
Thank you. Bye.
Okay. So our next speaker is with us. We'll take a 5 minutes break, and maybe we'll start our session next talk just after 5 minutes. That is 11:30. Okay. So don't log out. You can still log in, and we'll start our next session after 5 minutes. Dr. Bose Subhankar, is that okay? I mean, can you start after 5 minutes?
Yeah, sure, sure. No issue.
Okay, okay. So attendance link will be posted in the chat box during this talk. Okay. So during second talk, that is the talk of Dr. Bose, the attendance link will be posted. So we'll start our next talk sharp at 11:30. So I welcome all of you to the second talk of the session. In this session, we have with us Dr. Shubhankar Kumar Bose. Dr. Bose was born in Sikar, Rajasthan. He has received his MSc degree from the University of Rajasthan in the year 2004, and he got his PhD degree in 2011 from IIT Madras under the supervision of Dr. Sundar Gopal Ghosh, and he was awarded with the best thesis award in that year. So in the same year, he was awarded with a prestigious postdoctoral fellowship from Alexander von Humboldt Foundation, that is ABH Foundation, and he joined the research group of Professor Todd Mader at the University of Augsburg, Germany, and he continued his postdoctoral research in the same group till January 2017. In February 2017, he began his independent research career as an assistant professor at the Center for Nano and Material Sciences, Jain University, Bangalore. His current research interests focus mainly on organometallic chemistry, catalysis and synthesis, structure and bonding of transition metal main group compounds. Dr. Ghosh has more than 50 publications in the leading international journals such as Science, Angioantachemy, ACS Catalysis, Green Chemistry, Organic Letters, etc. So he was my lab mate, and we both did PhD under the supervision of Dr. Ghosh. So he's a very good friend of mine. So today he will be speaking on reusable nanocatalysis and efficient and selective synthesis of organoboron derivatives. So with this short biodata, I request Dr. Bose to kindly go ahead with his presentation. Dr. Bose, the floor is yours.
Yeah, Dr. Sahu, thank you so much for your kind introduction as well as a kind invitation. So my slide is visible, right?
They're absolutely visible.
Yeah. So thank you so much, the coordinator and the convener, my good friend Sahu. I know him from last 14 years, 2007 when I joined the IIT Madras. So thank you, Sahu. So today I'm going to talk about after the very nice talk from the Professor Garpure, which was mainly the hardcore synthetic chemist. And you saw a different way of synthesizing the drug molecule or the medicinal important molecule. So similarly, the organoborane derivatives are a different class of organic compounds, which are also coming to the organic synthesis. And what I am going to trying today is using a reusable nanocatalyst for the synthesis of these derivatives. So before going to talk about my own research, I would like to put some light on the previous history. And the organoborane compounds is nothing but compound having carbon-boron bond. And the
sorry to interrupt. I mean, can you make the screen, full screen?
Yeah, it is full screen. Yeah, is there any way? So I put it full screen only. I'll do it 1 minute.
Yeah, please.
So actually, I'm not very familiar with this Google. So should I go for entire screen?
Yeah, you can go ahead with the entire screen. Yeah.
Mm-hmm. No, that won't work.
you can go ahead with present, I mean, just one window, but make it like full screen. I mean, the screen can be bigger.
Okay, so now it is in the short form, right?
Yeah, yeah.
And-
Just yes, that icon. Yeah, fine.
And now it is fine?
It will come probably. You are clicking it.
Now, is it okay?
Still, I mean, it is in that like
No,
the
that
slides
mode
are
only.
showing. Yeah.
But I made it, okay, I'll just do one thing.
Yes, it is there. It is there. Please go ahead.
Now
It's
it's
fine.
okay?
Yeah, now it's fine. Yeah. Go ahead.
Okay, yeah. Okay, so I'm talking about the organoborane synthesis, and in 1956, with the presence of one of very brilliant Indian postdoc, Dr. Subba Rao, the H.C. Brown has invented the reaction called hydroboration reaction of carbon-carbon and multiple bonds. And from this reaction, what they found that the reaction was very fast, and the addition of the BH bond to the carbon-carbon double bond is in very stereoselective, added at the less hindered side, and giving the anti-Markovnikov addition product, where the boron is added to the less substituted carbon, which leads to further oxidation, the primary alcohol. During that time, 1950s, people were very interested to get the primary alcohol, which was not easily can achieve using the Markovnikov addition reaction. So these reactions were very important, not only based on their regioselectivity or stereospecifics in addition, but also once you have this carbon-boron bond, you can derivatize it, you can convert this carbon-boron bond to the alcohol and to the different halide groups, amides, amines, and so on. And that is the reason that H.C. Brown got the Nobel Prize in 1979 for the invention of, or the usefulness of these organoborane compounds. Not only this, you can synthesize the organoborane derivatives following the hydroboration reaction, but also using very reactive organolithium and Grignard reagent, which we all know in our UZ classes, we read about the Grignard reagent. If you just react with the suitable boron reagent and further trans-esterifications, if you perform that, you can get these organoborane derivatives. But the problem was, these reactions are very sensitive towards air and moisture, and moreover, all the boron reagents are monoboranes, BS3 or B2H6, or the stabilized borane adducts, which were very sensitive towards temperature as well as air and moisture. And more, because of that, not much functional group has been tolerated by this reaction. So researcher, they found that instead of using this reactive monoborane or diborane reagent, can we use the stable diborane reagent, which I have shown here, the bis-pinicolated diborane, bis-catecholato diborane, or bis-neopentylated diborane, which you can see the diboranes, because of the back bonding from the lone pair of the oxygen, these borons are very stable, and even you can handle these diborane in air. And particularly because of their popularity, you have access these diborane in commercially as well. And towards this B2PIN2, this bis-pinicolated diborane has been used extensively. After having these diborane reagents, the problem was to activate it, because monoboranes are what H.C. Brown or the previous scientists has been used. They were very reactive, and you can get the organoborane derivatives, but these diboranes are not very reactive. So you need some catalyst to activate that. And so So people start to use a metal-mediated organoborane synthesis, and in towards this earlier report shows that precious metal like platinum is mostly has been used. So here you can see the platinum where in zero oxidation state easily go oxidative addition reaction to the diborane compounds and giving this platinum boryl complex, where this boron got a partial negative charge and which can insert to the carbon-carbon multiple bond, and reductive elimination reaction gives the organoborane derivatives and regenerate the catalyst. And importantly, the selectivity is quite complementary, and not only the alkene or alkyne or other unsaturated organic substrate, but also very unreactive alkanes also can be easily activated using this diborane, can be activated using this precious catalyst in presence of B2PEN2, and they got selectively the terminal CH activation product, the alkyl boronate esters. And that was the first report by the Hartwig in 1999. In the same year, the Smith and co-workers found that even the sp2 hybrid, the benzene CH bond, which is also very unstable, very unreactive, also can go for the CH activation or CH borylation reaction using iridium as a catalyst. And that was the major breakthrough during that time. So there was a lot of literatures come on the in the 90s and 2000s, and even the later on in the early year of 2010 as well. So the main application, what they found that this organoborane compounds or different organoborane derivatives can be a coupling partner in the CC coupling reaction in presence of palladium as a catalyst, which the Suzuki has invented and got the Nobel Prize in 2010. I'll just show you why he got the Nobel Prize. Because of this coupling reaction, and where the palladium in the zero oxidation state has been used as a catalyst, and the aryl halide or alkyl halide in the first step will go for the oxidative addition reaction and give this palladium +2 intermediate, followed by transmetallation using where the organoboranes has been used in the presence of base. The nucleophilic carbon partner has been transferred to the metal center. And the further reductive elimination gives the CC coupling product and regenerate the catalyst. The reason the organoborane derivatives become so popular was they are very mild organic Lewis acid, they are very stable, and you can easily derivatize it and easy to handle it as like organic compounds, and they are very less toxic. So you can prepare a range of derivatives of these organoborane compounds using different method, which I'm going to talk about today. And because of that reason, this reaction become popular. Not only that, this coupling reactions has been used extensively by the pharmaceutical industry as well as agrochemicals. Here I have shown few of the example. This valsartan, which is an antihypertensive drug, and has been synthesized using this Suzuki CC coupling reaction, and the reaction was very neat, and because of that reason, the price of these medicinal important drugs has been low down because of very few steps to synthesize it. Also, another example which I have shown here is losartan, which is also has been synthesized using Suzuki coupling reaction. First, you have to prepare these organoborane derivatives, and then a suitable coupling partner when it comes and make the CC bond gives this important antihypertensive drug molecule. Not only that, this organoborane derivatives is very useful in only the CC coupling reaction as a coupling partner, but they are in the market currently where the boron containing drugs are in commercially available for the anti-cancer therapy. One of the example I have shown this Bortezomib, which is in the market, as well as type 2 diabetes for there also deutoglymptin has been used extensively and in the market, our antifungal agent, where all the drug molecule you can see that there are boric acid a moiety, which is playing an important role to show this medicinal importance of this molecule. As a synthetic chemist, which we are always looking for the importance of the molecule. So if compare in the point of view synthesis, this organoborane derivatives can very easily derivatize from CB bond to the different halide groups and alcohol, acid, cyanide, ethers, amides, and CC coupling product, and so on. So these are the some few example I have shown there, where the organoborane compounds or derivatives has been used extensively. Not only that, in material chemistry, in OLED, and in agrochemical chemistry, in pharmaceutical as well, these derivatives has been extensively used. And if you see the synthesis of these derivatives, mostly I have also shown that the iridium and the rhenium, the catalyzed reaction of palladium and platinum catalyzed reaction are initially in 2000 and 2005, they have been used mostly this precious metal catalyzed organoborane synthesis. But later, in last decade, people mostly concentrate on the first two transition metal, particularly iron, cobalt, nickel, and copper and zinc. And the reason behind is very, very simple, that they are very cheap and they are earth abundant, and environmentally they are very friendly. They are less toxic in compared to the precious metal. And because of that reason, this the first two transition metal catalyzed organoborane synthesis are become so popular in last 1 decade. And towards this, we also started our research when I took my postdoc position. So we thought that why not we can use the zinc as a catalyst, and we have successfully used the zinc, very commercially available zinc halide as a metal precursor in presence of NHC ligand, and we have successfully synthesized a series of boronates and boric acid derivatives. So we have successfully have done this alkyl halide CH activation.
Sorry to interrupt.
Yeah.
Maybe some network issue or some problem. Your slides are not moving actually. I mean, it's still in that HC Brown slide.
Oh, is it? I'm sorry for that. So I think I should stop sharing and share it again. Okay, is it visible now?
Yeah, it will come. Yeah, now it is there. But yeah.
It is moving now?
Yeah, now it is slide 4, 5. Yeah.
Yeah. So when I put in the full screen, I think there is a technical problem. It is not moving. Okay. So I won't put it in the full screen. So now it's fine, right?
Yeah, now it is slide 8. Yeah.
Right. Yeah. Okay, so I was talking about the first row transition metal, particularly the iron, cobalt, and nickel, copper, and zinc, where people were more interested to use this non-precious metal as a catalyst because they are cheap and earth abundant and they are less toxic. And towards this, we also started to use the zinc as a metal precursor and try to explore that whether or not this zinc can be used for the catalytic reaction for organoborane synthesis derivatives. And towards this, we have successfully, we proved that zinc chloride in presence of NHC ligand, alkali halide correlation we have been achieved. Also the aryl halide sp2CX activation also has been done using zinc dibromide, zinc bromide as a metal precursor. And when we have changed the ligand from NHC to the ditertiary bipyridine, the bidentate ligand, what we saw that not only the CX bond, but also ortho to the CX, the CH bond also can be activated using the zinc catalyst in presence of DTPY as a ligand. Also, we have shown that copper 2 can be used for alkyl halide borylation. Copper-2 is more important and more user-friendly because they are more stable in compared to the copper-1, where they easily oxidize to the copper-2. So when you use the copper-2 metal precursor, so we can able to do this alkyl halide borylation using the NSCSL ligand, and has been synthesized a series of alkyl boronates. Yeah, so during that time, I was very much familiar with these organoborane compounds and their derivatives. And when I took my independent research position, what I observed that the nanoparticle or recyclable catalyst using as a catalyst for the organoborane derivatives are very limited. And we have summarized that, and we found that only few examples are known where this nanoparticle has been used to synthesize a range of in organoborane derivative synthesis via diboration reactions or CX activation reaction or alkyl halide or alkane or aryl halide CH activation, or hydroboration of alkene or alkyne, or silaboration of the alkene or alkyne also has been used in very limited substrate scope. So knowing this fact, we took this challenge that whether or not we can extend or expand the substrate scope using a nanoparticle catalyst for the synthesis of organoborane derivatives. And towards this, first we started with the alkyl halide CH activation to synthesize alkyl boronates. And these alkyl boronates are also very important, having a importance in medicinal chemistry, and also they are a coupling partner in CC coupling reaction. These are the 4 different ways you can achieve these alkyl boronates. One, as I have shown in the previous slide, that if you can use this very reactive alkyl lithium or Grignard reagent and react with the reactive boron compounds, you can get this alkyl boronates, but they have their own limitation. And alkene hydroboration is another way to achieve this alkyl boronates, which also I'm going to talk about today. And this beta borylation, addition of the boronates at the beta position of alpha beta unsaturated carbonyl compounds, is another way to synthesize these alkyl boronates. Of course, the CH activation using precious metal is also a way to synthesize alkyl boronates, but we are trying to explore this currently in our lab, whether or not can we do it for using the nanoparticle as a catalyst. So today I'm going to basically talk about this direct alkyl halide CX borylation, which is a very useful tool to synthesize alkyl boronates because you can put the boron at a particular position where the halogens are present. Also, I'll talk about the hydroboration and the beta borylation reaction and other hydroboration of unsaturated carbonyl compounds as well. So in case of alkyl halide, the homogeneous catalyst is very well known, and copper, palladium, nickel, and zinc as already reported. But in case of, if you see in the heterogeneous catalyst system, only 2 reports were there. And that was also 2014 and 15. And the problem was only the alkyl bromides, which are quite expensive. If you go further to buy this, the starting precursor only has been used for this synthesis of alkyl boronates. So there was some limitation that not much functional group has been tolerated in both the reports, as well as the alkyl halides is limited to the bromide and iodide. So we set our target to explore to alkyl chlorides. Can we do it using a different nanoparticle as a catalyst? And for that, we have synthesized this functionalized copper nanoparticle and characterize it with the FESM, TEM, powder XRD, EDAX, XPS, and ICP analysis, and which shows that and took this catalyst for the alkyl halide borylation reaction, and using this 2-bromo ethyl benzene as a model substrate. And we started to use this B2Pin2 as a diborane reagent. And here you can see a series of different conditions we have been screened. When we use this copper nanoparticle in presence of potassium terbutoxide as a base, which is an activator to activate the BB bond in DMF as a solvent, given this, this alkyl boronates in the 94% yield. But when we use just Fe3O4 nanoparticle or Fe3O4 DOPA nanoparticle, which gives the very low yield of the alkyl boronates. In absence of any catalyst, it gives a very low yield of alkyl boronates. Further changing this, the activator potassium terbutoxide to the sodium terbutoxide or lithium terbutoxide, potassium methoxide or sodium methoxide, giving lower yield of alkyl boronate. In absence of base, there were no product at all. And using different solvent like THF, toluene, and DMA and acetonitrile also were not so profitable. So based on that, what we found that when we increase the amount of the B2Pin2 from 1.2 to 1.3 equivalent and the base as well, in an 18 hours reaction at the room temperature gives the quantitative yield of this alkyl boronates. Moreover, the reaction is quite feasible in air as well. You can do the reaction in air and got the good yield of alkyl boronates, which is very important points to make it, because the homogeneous catalyst systems are mostly very sensitive towards the air and moisture, but here we can do it in the reaction in air as well. Okay, so after having this best condition in our hand, we explore a range of alkyl halides. And here you can see the primary alkyl halides having the bromides, having different functional group like ester, ketal, methoxy group, and in the presence of other halides also, the reaction is quite feasible and giving the alkyl boronates in good to excellent yield. Moreover, the secondary alkyl halide, which is not so easy to borylate, also possible using this system and giving the alkyl boronates in very good yield. There was a limitation that tertiary alkyl halide reaction was quite sluggish and giving a very low yield of alkyl boronates. As I mentioned that our target was to explore the alkyl chlorides. So towards this, after the intensive screening, what we found that if you add this tertiary butyl ammonium iodide as an additive, we can able to do these alkyl chlorides, which are very cheap to buy commercially, and we can borylate that, and having different functional groups like methoxy, alcohols, and the indol, carbazole, thiophene, and even the dichloromethane, which is very frequently used in the laboratory, chemistry laboratory, can be borylate using our system. And activated benzyl chlorides and bromides also has been borylate in good to excellent yield. Not only that, this diborane, instead of B2Pin2, we can change to the B2Neop2 and giving this alkyl boronate in excellent yield. After that, we try to explore the main importance of this nanoparticle, which is reusability. That was the main limitation of the homogeneous catalyst system, that we cannot reuse the catalyst or the expensive catalyst or sometimes expensive ligand. But in our case, we can actually recycle it up to at least up to 10th cycle without any decrease in the activity of the catalyst. And very simple way, just apply the magnet, and you can just filter the reaction mixture and wash this catalyst, and then it's ready to use for the next cycle. Also, we have proved that this the heterogeneous nanoparticle is an active catalyst by the mercury poisoning experiment, which shows that if you add this mercury, which actually deactivate the active site of the nanoparticle, and because of that, there was no product observed for the alkyl halide borylation reaction in our condition in presence of mercury. Also, we would like to find it out what may be the possible mechanism of this alkyl hydroborylation reaction. So towards this, first we start to use this 6-bromo-1-hexene, which is very well known for the radical clock experiment. And in presence of radical, this substrate is very well known to go for cyclization reaction. So when we use this as a substrate, what we saw that along with the normal, the CX borylation product, along with that we can see some cyclized product as well, which is almost 85% yield, which shows that or suggests that there is a radical mediated process. Interestingly, when we took this cyclopropyl methyl bromide as a substrate, which under the standard reaction condition, give exclusively ring opening product, again shows that that there are some radicals are present in the reaction mixture. And to confirm that, we perform the reaction in presence of radical scavenger using this 9,10-dihydroanthracene and as well as TAMPO, which shows that this addition of this radical scavenger in the reaction mixture stopped the reaction almost completely. And moreover, after the careful analysis of the reaction mixture of this TAMPO added reaction mixture, what we saw that there was a TAMPO adduct with the our alkyl halides, which further confirmed that there was a formation of the radical which has been trapped by this TAMPO. Okay, so further, after successful exploring the alkyl halide borylation reaction, another way to synthesize alkyl boronates is the hydroboration reaction, which is actually regio and stereo selective reaction and can get this alkyl boronates in very good yield. So towards this, after the extensive screening, what we found that in presence of potassium terbutaoxide and methanol as an additive in DMF solvent, this styrene derivatives can be easily hydroborate in very good yield. And here you can see the electron-rich methyl methoxy group halides, leptin deficient, and carbazole, and even the sterically hindered 2,4,6-trimethyl styrene derivatives also borylate given the hydroborated product in good yield. Also, internal alkene also has been hydroborated in the good yield. So in this system also we saw the reusability of the catalyst, and we found that up to at least up to five cycle catalyst can be reused without any decrease in the activity of the catalyst and the decrease in the hydroboration product amount. Further, we also try to find it out what may be the possible mechanism, whether or not this is also going by a radical process. For that, what we have done is we took this vinyl cyclopentane as a substrate, which is actually known to go for the ring opening product in presence of radical reaction. So when we use this substrate along with the normal hydroborated product, we did not observe any ring opening product, but instead of that, we observe this cyclohexyl methyl boronates, which probably has been formed via ring opening followed by ring closing, which gives the 6-member cyclohexyl methyl boronates as a main product. And this is a GC spectra of that, where you can see the both having the same mass, and this has been isolated in 37% yield. Okay, so to confirm further, we perform the reaction in presence of radical scavenger, the same 9,10-dihydroanthracene and TAMPO as a radical trapping agent. And when we perform this reaction, we got very low yield, and in TAMPO case, we did not see even the formation of the hydroborated product, which further confirmed that this process also probably going by a radical process. To to confirm that whether or not this, as we are using HP pin, B2Pin2 and the base as well as in presence of methanol, whether in situ HP pin formation has taken place or not. So we took the, instead of B2Pin2, this Pinnacle Boron we have used as a source of boron, and we performed the reaction, and which shows that there is a no hydroborated product form, which confirmed that actually the B2Pin2 is a source of diboron compound, it is not converting into the HP pin and giving the hydroborated product. From this, I would like to go for another way of synthesizing alkyl boronates, where you can do the formation of put the boronates at the beta position of alpha beta carbonyl compounds selectively using the metal as a catalyst. And in our approach, we use this copper nanoparticle as a catalyst in presence of potassium carbonate as an activator, methanol as an additive. After the best condition we had, we perform a series of alpha beta unsaturated carbonyl compound, which shows that this system is quite compatible with the electron withdrawing as well as electron rich alpha beta unsaturated ketones, as well as this is quite compatible with the ester as well as the aldehyde substrate as well, which is one of the very unique catalyst system which we have reported, where we can do the beta borylation of not only ketone but also ester and as well as aldehyde. And also we proved that the reaction is again the catalyst is recyclable up to 5 cycle and can be recovered it and can be reused it without loss in the activity. As we have used the methanol as an additive as a source of the hydrogen, so when we replace this methanol with the deuterated methanol, what we found that there is a deuteration incorporation at the alpha position, which confirmed that the hydrogen is given by the methanol only. So that is hydrogen isotope labeling experiments, which confirm that this methanol is a source of hydrogen. Okay. From this, I'd like to move on the another part where we have successfully established that this nanoparticle can be used for the reduction of not only the carbon-carbon double bond or the triple bond, but also we can extend to the carbon double bond oxygen and carbon double bond nitrogen as well. This carbonyl or aldehyde ketone reductions, you can easily do it using very active boron reagents. Even sodium borohydride also can use it, which give this borate ester and followed by hydrolysis give this respective alcohol. The problem is the presence of other reducible functional group, which is not compatible when you are using activated reducing agent like sodium borohydride or so. So people start to use as a catalyst for this process, and here you can see in presence of catalyst, you can do the hydroboration of this carbonyl CO double bond and give this borate ester, and followed by the hydrolysis give this respective alcohols. And towards this, recently in last 10 years, there was a numerous literature come where they have used the transition metal. Or not only that, the main group elements as well as F block elements has been extensively used for this type of hydroboration reaction. And what we would like to do is we want to use as a iron as a catalyst. And why iron? Because the iron is quite abundant, is less toxic, and the price is very low. And if you see in the homogeneous iron catalyzed carbonyl reduction, there were some few reports where they have been used the iron as a catalyst in a homogeneous way, but more or less all the iron catalyst has been synthesized in multi-step process, and you have to keep the environment air and moisture free. So to know that, so we thought that why don't we can use this nanoparticle or recyclable catalyst, and we saw that in the literature there were some few reports where they use the recyclable catalyst like zirconium supported, silica supported zirconium catalyst, iron and the cobalt on the copolymer as a catalyst, and the cobalt, magnesium, titanium on metal organic framework as a recyclable catalyst for the reduction of these carbonyl compounds. And what we have done is, instead of a multi-step process of the catalyst, we try to explore that can we do it with the iron oxide, which is very straightforward to synthesize it. After synthesis, we have been characterize it with the Fe, SEM, TEM, and powder XRD and E-, which shows that purity of the compound or the nanoparticle catalyst. And we start to screen the reaction conditions. And here you can see when we took this HP pinicoborane as a boron reagent and benzaldehyde as a model substrate, using Fe2O3 nanoparticle as a catalyst, in 1 hour it giving only 54% of the borate ester. But when we increase the time from up to the 8 hours at the room temperature, stirring gives the quantitative yield of the borate ester. Commercially available, the iron salt like FeCl3 or FeNO3, ferric nitrate, or even the bulky Fe2O3 is also not very useful to convert or to give the borate ester in good yield. And FeBr2 also as well has given very low yield of borate ester. In absence of any catalyst, it gives very low amount of borate ester, which shows that which exclude the uncatalytic reaction in this system. Further, we, instead of using 1.2 equivalent of HPPin, we use 1 equivalent of the pinicoborane, which giving the less amount of this borate ester. But also we would like to see that whether or not we can go for the lower loading of this Fe2O3 nanoparticle, so which gives the lower yield when we use the 1 and 3 mole% of the catalyst. So the best optimized condition what we found is using 5 mole% of iron nanoparticle, using 1.2 equivalent of pinicoborane, 8 hours for the hydroboration of the aldehyde substrates. Further, I'd like to mention that that reaction is quite compatible when we perform the reaction in air, which shows that 90% of the borate ester we can achieve when we perform the reaction in air in absence of nitrogen atmosphere, which is really good. So having this best condition in our hand, we explore the aldehyde substrates, and here, so here you can see we can actually do the hydroboration of electronically rich aldehyde like methyl, methoxy, and alcohol group, but also this fluoride, chloride, bromide, which are the electron deficient aldehydes, also can be hydroborated using our system. Important thing is the functional group can be reduced during this process, like cyanide and nitro groups, can also hydroborate using iron oxide nanoparticle as a catalyst. Sterically hindered orthosubstituted group also has been hydroborate in quantitative yield, and this cinnamaldehyde, which is alpha beta unsaturated aldehyde, instead of going to 1,4 addition product, it gives exclusively carbonyl reduction product, which is also very important in this system. Also alkyl halide benzyl carbonyl compounds also has been reduced in very good yield using this system. Further, along with the aldehyde, we next move to the ketone reactions, and using this nanoparticle, we can easily reduce the ketone as well, but we need a little longer reaction time, 18 hours, because of the steric hindrance created by the 2R groups. So electronically rich substrate and the deficients and even the alkyl group having ketone also can hydroborate it using this iron oxide nanoparticle as a catalyst. So that was very good. And not only that, we try to show that utility of this nanoparticle catalyzed hydroboration reaction. So this reaction can be performed in gram scale. And here you can see this 4-bromo-benzaldehyde, even the orthosubstituted benzaldehyde and the naphthaldehyde also can be hydroborated and convert into the alcohol in very good yield. So which shows that this nanoparticle is not only the small scale reaction, also can do the hydroboration of aldehyde in the gram scale as well. The main challenge of this catalytic hydroboration reaction is the reductions of the carbonyl compound very selectively in the presence of other reducible functional group. To prove that our system is also compatible with this in presence of other reducible functional group, we have done some competitive intermolecular and as well as intramolecular. In intermolecular competitive experiment, when we have chosen this the aldehyde and ketone mixture of that, irrespective of the electronic effect, the aldehyde has reduced preferentially in compared to the ketone. Not only that, in the intramolecular, having in one substrate itself the ketone, esters, and amide, when we have used this substrate, selectively give the hydroboration of this CO bond, carbonyl aldehyde CO reduction bond, in the presence of even the ester and the amide CO bond, which shows that high chemoselectivity of this iron oxide nanoparticle catalyst systems. Also, when we have mixed this different electronic nature of the aldehydes, shows that it hydroborated electron deficient substrate more in compared to the neutral than the electron rich substrate. Which all the experiment proved that our nanoparticle catalyst systems for the carbonyl reduction is quite comparable with homogeneous catalyst system. Also, we would like to know that what may be the possible mechanism, and as we weren't able to do the NMR monitoring experiment because of the heterogeneous nature of the catalyst as well as the paramagnetic nature, we just try to follow the reaction via the IR spectroscopy, which shows that when we added in stoichiometry amount the catalyst and the substrate, the aldehyde, there was some interaction. So, which shows that there is the first step would be there is an interaction between the catalyst and the substrate, and followed by the addition of the HPPin, which gives the borate ester and regenerate the catalyst. During this, when we are doing this iron oxide and particle catalyst carbonyl reduction, what we found that there were no reports on the nanocatalyzed F-block element using for this carbonyl reduction, and we choose cerium because it is abundant and has been extensively used in many applications in heterogeneous catalyst system and many other applications. So here I have listed a few of the F-block complex which has been used as a homogeneous catalyst for the carbonyl reduction. So here you can easily find it out that these catalyst synthesis multi-step, as well as you have to maintain the inert atmosphere to synthesize this F-block metal complex. So in our contribution, what we have done is we just synthesize the cerium oxide nanoparticle and use for this carbonyl reduction. And after having extensive screening, what we found that this 10 mole% of the cerium oxide nanoparticle in presence of 1.3 equivalent of HPPin in MTBE, methyl tertiary butyl ether as a solvent in 24 hours at room temperature is best condition to reduce this the aldehyde CO bond. And here you can see a series of aldehyde electronically rich, like methyl, methoxy, and NME2 groups are hydroborated using our system as well as electronic deficient. Also, the nitro and cyano groups were intact when we have used our system for the carbonyl reduction. Okay. Not only that, this cinnamaldehyde is again has been reduced selectively on the only CO double bond in the absence of CC double bond. So which shows that very high chemoselectivity of this catalyst system. Not only the aryl halide aldehydes, but also alkyl derivatives also can be hydroborated using this system. And the ketones are also a very good number of the ketone has been reduced using this cerium oxide nanoparticle as a catalyst, but we need to heat it up to 50 degree and 24 hours reaction time. And here you can see a series of this ketone has been reduced with excellent yield. And not only that, this alkyl derivatives also and the heteroarenes also has been reduced using the cerium dioxide nanoparticle as a catalyst. And as the selective reduction is very important, so we examine for the cerium oxide catalyst system as well, and it shows that in presence of intermolecular competitive experiment shows that the aldehyde is selectively reduced in presence of the ketone. Again, it is very selective, but also we have expanded that the competitive experiment, and when we mix this aldehyde in presence of alkene, styrene, and the phenylacetylene, which shows that this catalyst system is very useful to reduce selectively the carbonyl CO bond. When we have used this benzaldehyde and styrene, we got selective reduction of the benzaldehyde only, and the styrene was intact, which has been confirmed by the GC-mass and the proton NMR analysis. And also similarly for the ketone and the styrene, when we mixed up, similar result we have found that the reduction is taking place at the carbonyl CO double bond only in presence of carbon-carbon double bond. Similarly, for the acetylene, when we have mixed, so it reduced the carbonyl group as only, and this acetylene triple bond, CC triple bond has become intact. So which show these results shows that this catalytic system is highly chemoselective and selective towards the carbonyl reduction. Intramolecular experiment shows that this selectivity is towards the aldehyde when you have the aldehyde and ketone functional groups in same substrate, and even the esters and amides, presence of ester and amides also giving this aldehyde CO reduction exclusively. When we have reduced this, having the cyanide group in the same functional group also has reduced the ketonic C double bond O, and in presence of alkene double bond and as well as nitro group also the hydroboration take place the carbonyl C double bond O only. So these results shows that this reaction is really very chemoselective and compatible with the homogeneous catalyst system. Also, we compare the earlier previous results where they have shown that BS3 mediated reduction can be done for the carbonyl reduction, and that is the main advantage of catalytic carbonyl reduction, that the other reducible functional groups like nitro or even the alkene groups are intact when we are using metal as a catalyst. So when we use the BS3-THF as a catalyst, which shows that the nitro group has been reduced as well as carbonyl, and when we just mix the intermolecular competitive experiment, in that we found the benzaldehyde as well as styrene, both has been reduced and when we use a BS3-THF as a reducing catalyst. So which shows that this nanoparticle catalyzed system is quite efficient and chemoselective and comparable with the homogeneous catalyst system. So more importantly, the reaction is quite recyclable. The catalyst is recyclable up to 2 cycle. There was no decrease in the yield, but after that, up to 10 cycle, there was some small amount of the we got the little small amount of the yield, which is 78%. But after the 10th cycle, when we recycle the catalyst, and after the recovering the catalyst, we have calcined it and reuse this catalyst for the further reduction reaction. So which shows that the catalyst is again reactivated and can be used as efficient like a first cycle. And this is the FESM image of the calcined after the recovered 10 cycle catalyst, which shows that there is no change in the morphology of the catalyst. We also try to find out what may be the possible mechanism, and we follow with the IR spectroscopy because the NMR was not that informative because of the heterogeneous nature of the catalyst. So IR shows that there is an interaction between the metal oxide nanoparticle with the substrate, which changed the IR wave number to the lower wave number, and further reaction with the HB pin, which may go via the sigma bond metathesis reaction, may give this intermediate, this borate ester, and leave this product and regenerate the catalyst for the next cycle. So this is our possible catalytic cycle, which also has been reported in the homogeneous catalyst system. So we propose that our system is quite comparable or the similar way the reaction is going in case of metal oxide nanoparticle carbonyl reduction. Okay, from this I would like to summarize it, that we hope that I hope that I have shown that this nanoparticle catalyst can also be used as efficient as like a homogeneous catalyst system, and we have successfully synthesized a series of alkyl boronate derivatives using a different method. So alkyl halide borylation has been achieved using this copper nanoparticle as a catalyst. Also, the styrene derivatives has been hydroborated, as well as beta borylation has been achieved using a series of alpha beta unsaturated carbonyl compounds and giving this alkyl boronates in excellent yield. Also, these metal oxide nanoparticles are quite comparable, efficient, and reusable in compared to the homogeneous catalyst system, and giving a range of reduction product in excellent yield, which we have used Fe2O3 nanoparticle and silicon dioxide as a nanoparticle. Okay, from this, I'd like to thanks my co-workers. So most of the work has been done by my first PhD student. He was recently graduated, Mahadev. He is now Dr. Mahadev. And also, we have a master's student, and our center is dedicated to the research that from day one onwards, master's students are exposed to the research. So their projects start from first semester itself. And also, I'd like to thanks my collaborator for their help to get the characterizations done for our research work, and funding agency, SCRP, and startup grant from the Jain University. Also, before I finish, I would like to show that where we are situated. Our main campus is far from the city. It's quite almost 85 kilometers from the Bangalore airport, and it's quite big and nature around. And our center is in this fourth floor and the top floor, and which is dedicated to the research only. We are pursuing carrying out only the master, and only the PhD and the postdocs students are there in our center. Okay, so I would like to invite you there. If you get chance to visit in Bangalore, please stop by. Of course, this is not good time to give an invitation during this pandemic, but definitely the situation will improve, and definitely we can meet in physical mode as well. yeah, from this, I'd like to thank all of you for your kind attention. I would be very happy to take few questions. Yeah. Thank you.
Okay, thank you, Dr. Bose, for your presentation. Now the presentation is open for discussion. So any question from the participants? Dr. Bose will be very happy to take, few questions. There is one question in the chat box.
Yeah.
You do your reaction is in toluene. So why so specific? Some of the catalytic reactions.
If you see in the alkyl halide project, so we use a DMF. So other solvents were not that good. People prefer to use toluene or DMF because in that case, the nanoparticles are dispersed very properly in the reaction mixture. So, and that is the reason maybe the substrate can interact with the nanoparticle more efficiently in compared to the other organic solvent like ether or THF or MTB. So what I guess, or as in also in the reports, that the DMF and in the toluene, the nanoparticles are dispersed far better than the other solvent.
Okay. Any more questions from the students or audience?
Hello, sir. I have one question.
Yeah, please.
Sir, what is HB pin? And the second question is, what are the applications of alkyl boronate compounds?
Okay, so probably I have mentioned some of them. See, HBpin is another boron reagents, like if I have shown in the previous slide, the diborane reagent. Similarly, HBpin has been used as a boron reagent to introduce the boronates to the organic substrate. So this is more economically useful, fruitful, I would say, because we are using one boron reagent and which is adding to the organic substrate. So, and the product also having a one boron and organic substrate. So economically, this reaction is more useful in compared to the diborane reagent. But sometimes the only disadvantage of using HBpin is you need the inert atmosphere to keep this pinnacle borane. So you have to keep it in nitrogen atmosphere. But in diborane compounds, B2PIN2, you don't need to, even you can keep it in the outside instead of dry box, you can just keep it in like organic reagents. Another questions what you have asked is alkyl boronates are also similarly used. So initially when Suzuki invented this CC coupling reaction, which is only the sp2 carbon boronates and the sp2 aryl halides, but later on they expanded that not only this aryl boronates but alkyl boronates also can be used for the CC coupling reaction. And also you can see here in some of the molecule where the boron is present, and they have this boron in the alkyl skeleton. So which also shows that these alkyl boronates are very useful. So this invention or this discovery is not before that Hartwig come up with this direct alkane CH activation reaction, which I have shown here. I'll go here. Yeah. So that was the major breakthrough when he can do this alkane terminal CH bond selectively the alkyl boronates. So I hope that I answered your question.
Thank you very much, sir.
There is one more question. What is, just let me read that. What is the actual amount of hydrogen produced from metal mediated boronation reaction?
You mean in this reaction, right? So
it is in the chat box.
yeah. So in our reaction where we are using alkyl halide, so we are just activating the CX bond, right? So here, if you see the alkyl CX bond, so halogen has been taken out. So and the boron, so there is no hydrogen elimination in the reaction. But when this Hartwig as well as the Smith has done this direct CH activation of this the benzene and benzene derivatives, they actually found that the based on the substrate, the amount of the hydrogen evaluation they have been observed. So they did not quantify that how much hydrogen has been evolved during the reaction, but in the closed reaction mixture NMR tube, they have found that, and they have characterized by the using the deuterated benzene that actually the HD has been formed. So I hope that I answered.
So is this particular reaction, so what is the better term to justify? Is it CH activation or BH activation or CH borylation?
See, in terms of the organic chemist, which they prefer to do that CH activation. So you can call this reaction, both the reaction alkane and the benzene, both the reaction is particularly CH activation. Where the CH bond has been activated in mediated by the metal center, and instead of the functionalization here, the boron has been introduced at a particular carbon skeleton. So
I'm talking about the bottom reaction. Yeah.
Yeah. So this is CH borylation reaction, and also you can say the CH activation. People actually is argue about whether this is functionalization or the CH borylation reaction, because you are functionalizing the benzene derivatives, which you can further use for the further derivatization. So people also prefer to call this a CH functionalization as well. So different scientists or the different literature, they have been used different word, but the boron chemist or the organoborane chemist, they prefer to call as a CH borylation reaction.
Okay. So any more questions? Probably they are tired of these 2.5 hours, 3 hours talk. I mean, two subsequent talks, and probably they are tired.
Yeah.
So, okay, if there are no more questions, let me join in thanking Dr. Bose for his beautiful presentation. So, thank you very much, Dr. Bose, for your time and for your presentation. It was beautiful and nice presentation. Thank you very much.
Yeah, Dr. Sahu, thank you so much for inviting me. And it was very nice to see you after a long time. We always talk on phone, not on the, at least now because of this, the virtual mode, at least we can see each other.
Okay,
thank
so
you. Thank you all of you.
Very nice. Okay, to see you after a long time. And if time permits, I mean, you can sometimes join us for a presentation for students, because some of our students are not present because of their examination. So
Right.
We would love to have you definitely sometimes in future. Thank you very much.
Definitely. It will be my great pleasure. I will be always available. You can just write to me anytime. Thank you, Sahu.
Thank you, sir. Thank you.
Yeah.
Okay.
Thank you.
Okay, so thank you very much, dear participants. So this ends our first session. So I hope you have received the feedback form for the first session. We will start our second session at 2 p.m. So we'll have last lecture. So kindly join before like 10 or 15 minutes. So probably we'll meet around 1:45 or 1:50. So till then, enjoy the launch time. Okay, so we'll meet you around 1:45 or 1:50. Thank you. Once again, I'm sharing the feedback link. So those who have not filled it, they can fill it. So we'll take a break and we'll meet maybe after 1 hour. Thank you very much.